Let's talk about section 5.4, exponential and logarithmic models. So in this section, what we're going to talk about is we're going to talk about modeling data for exponential functions as well as modeling with logarithmic. We're going to kind of compare a little bit between our different types of models. And then also we're going to kind of take a look at kind of that constant percent change to see whether or not it actually will fit. Again, we'll just kind of talk about that briefly there. So anytime we talk about models, the first thing that you got to remember, we've called this by multiple names, okay? We have called it the best fit line. Now that's when we were talking about linear regression, okay? So that's when it was called the best fit line. However, it could have also been called linear modeling. It could have been called linear regression. So we're kind of moving away from linear modeling and linear regression and moving into what we call exponential modeling or exponential regression. Okay, and we'll also tag in the logarithmic. Now we did this also a little bit earlier in previous sections with quadratic modeling or regression. Okay, so keep in mind that if I ever talk about find the linear model or find the exponential model or find the logarithmic regression, I can use kind of different wording for these, but they're all very similar. A good key thing to kind of let you know, and just as you're kind of looking at this now, if there's a chart like this, that is a strong indicator that it's going to be a model itself, okay? Or a style of regression. So anytime you see like charts like this, it's a really strong case for that in this course. So that's the first thing I want to kind of go, oh, right, I got a chart. Let me go ahead and put something in list 1 and something in list 2. Okay. Normally ages will be our list 1. So again, kind of a time frame there. And list 2 is going to be our other output, which is the monthly premium. So let's actually figure out what this chart is about. So the monthly premiums for $250,000 in term life insurance over a 10-year period increases with age of the men purchasing the insurance. Now below in our table is the monthly premium for non-smoking males are shown. So again, as we kind of take a peek at this idea here, if I am 35 years old, my monthly premium for 10 years for this life insurance will be $123. Okay. However, if I wait until I'm 50 years old to purchase this life insurance, I'm going to have to pay $338 for the next 10 years. Okay. So if you need to, go ahead and pause here, and that way you can plug this into your calculator. Like I said, we're going to kind of go through these a little quick because we've done things like this before. This is not new for us. Okay. So we're going to plug it in and we're going to do what we call a graph. Now, guys, do remember that a lot of the times your problems are just going to use the word like graph the data. But in our calculator, remind yourself that we call these by basically making a scatter plot. So if you need to remind yourself, first, you're going to put this stuff in list 1 and list 2, and then you're going to turn on your scatter plot. And remember to turn on your scatter plot, you're going to hit that second button, and then you're going to hit that y equals. Okay. And right above the y equals says stat plot. Okay. And that's what will help me graph all the data points itself. And it's going to be what we call a scatter plot because basically all of these points are going to be scattered against each other all over the graph. Okay. So again, this is going to be my list 1. There's my list 2. These are ages repeated here. So this is still going to be list 1. And again, these are just monthly premiums repeated. So that's list 2. Now, as I plug this into the calculator and I turn on my stat plot, I should get a graph that looks something like this. Okay. Now, as I'm taking a peek at this graph, one of the first things I see is that the points here kind of make this like upward hill motion. And so this is kind of maybe a good indicator that it's probably going to be an exponential just because it looks like our exponential style function. It doesn't really look that quadratic. I mean, it could be, but with quadratics, normally it's like it goes down and then up. So it's kind of got that U shape. This just looks like it just has this gradual going up, which is a little bit more like an exponential. Okay. So this is our data. This is going to be our scatter plot. And as we put it in, we're going to need to run a model. So let's run our regression here. Now to run a regression, again, make sure all your data is in list 1 and list 2. Please make sure that you have not deleted list 1 and list 2. It's very important that these actually, if you can just not delete the names of the list, then everything else will always be the same from here on out. So we go to Stat button. We're going to arrow over to the Calculate menu, which should allow us to see all those regressions that we've done previously, like the we've done the linear, we've done the quadratic. Okay. So we're just kind of adding on there. We're going to look for exponential. So again, that's going to be the EXP REG. It's under 0 itself. And your keyword to let you know that you're using exponential regression is just going to say an exponential model or an exponential regression. So again, they're going to use the word exponential in it. Let me go ahead and add this one in there. So if you'll take note of what number 9 was, number 9 says LNREG, which means linear, or sorry, not linear, logarithmic regression. And again, the keyword there in the problem will be the word logarithmic. So again, look for if it says a logarithmic model or logarithmic regression, then you're using this one instead. Okay. Now, everything should have been listed in list 1 and list 2. So therefore, when the pop-up menu happens, you're going to type in for list 1. It should automatically populate X list as list 1 and Y list as list 2. It should ask you a question about the frequency list. We normally leave that blank. And then if you want to store in reg equa, you can put it in Y sub 1. This will be the unrounded version if you do this, and then just hit calculate. For those of y'all that have my TI-83, okay, so this is going to be perfectly great for a TI-84, but for my TI-83s, just so we have an idea, all of the steps up to this point right here will be exactly the same, okay? But this point right here is kind of where you guys veer off. You're still going to do it, except for it's not going to have a pop-up menu. For the TI-84s, because they're upgraded, they have like this kind of like, oh, here's a pop-up menu, and like this is what you should have entered in. For the TI-83s, you kind of have to have it written down, like what exactly you need to type in. So for the TI-83, once you select that it's going to be like an exponential regression, it's just going to show on the home screen there, exponential regression. You're going to open up a set of parentheses and say list 1, comma, list 2. And then you can close it here and then just hit enter to calculate it. If you want to do the store reg equa, you totally can. So you would have to plug in the Y sub 1 there. And then once you've got that all done, just hit enter and execute and you should be good. And then it will show up with one of these two formulas here. So this is going to be my exponential regression model here. And it's going to be Y equals A times parentheses B to the power of X. And if it's a logarithmic regression, it's going to be this one down here. And again, logarithmic regression, even though it says LNREG, it's a logarithmic. It's just the very special form of natural log. Okay. And that's why it says LN there. Okay. Again, it will pop out an A and a B, which will let you know which one, what the numbers are. Be very careful on the rounding. It's very important to watch what it is asking you to round on these. Okay. So we're going to run that with our exponential function. And when you run that, you should have been given the following. So it should have simplified out rounding 4 decimal places to a 4.0389 parentheses 1.0946 to the power of X. Okay. If you want to put the X on the outside of the parentheses or on the inside attached to that number, either way is fine. It works just the same. Okay. And again, there's not a lot of work for you to do on these. So just remind yourself the calculator is doing the work for us. So now let's actually graph it. So we've got the scatter plot already turned on. So we're just going to go into Y equals, and actually this is what I'm going to plug into Y sub 1, which is my formula there. And we can see that the model is pretty okay. And I say pretty okay. And the only reason why I say it's pretty okay is if you take a look at like that point right there, that's like the only one that's not really touching it. It got close, but it's not perfect, which is where a model is only meant to be good for a short period of time. So as you can see at that very beginning part up here, it hits this point, it hits this, 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 this. And then here it kind of starts to veer away a little bit from it. And then this one's just kind of not even on it. So like this one's kind of far off the line. So it models like kind of where it should be, but maybe slightly off. Okay. Now, previously I talked about this constant percent change, and most people are like, I don't even know what you're talking about there. Please understand that when we talk about a constant percent change, that's basically asking about the different outputs. Now, all of our inputs should be equally spaced. And when I say inputs, those are those X values that we talked about, or the stuff that you put in list 1. Those are the input values. Those should be equally spaced, but the outputs that you have are not always so equally spaced. And so if they are perfectly constant percent change, then the exponential model will be perfect, which is not a normal real world scenario. But in the sake of math, sometimes we do create those just so you can get a good idea. But if it's maybe like, I don't know, somewhat approximately constant, but it may not necessarily be perfect, then that's where we're going to look at our exponential model really more. Okay. So suppose we've got a company and they're going to develop that released with some item, I don't know what it is, some product that is released with great expectations and extensive advertising. However, sales suffer because the bad word of mouth from a very dissatisfied customers. So below you can see in the table is monthly sales of data shown to the given percent change for each month is what we're going to start by finding. Okay. Now, again, as we see there, we can see in our months that we are taking these pretty much like pretty well what exactly is that increase amount is 1 month every time. So again, most data you're going to have kind of that simple where it changes from month to month. This should be pretty obvious that that input changes perfectly, but from here to here is what we don't know. And let's actually calculate that out. And it's a lot easier than you think. Okay. So what we do, the first thing we need to do is we really need to take a look at 780. And then we're going to take a look at this 608. So I'm going to take 780 minus 608, figure out exactly what is that change in the two. And I can see that I am decreasing it by 172. Now, I know that most of you guys are like, oh, but she said 780 minus 608. Again, we need to show like what direction the money is moving. So I'm going to put a negative on it because we know it's decreasing by that amount. So we're just going to take these two and see what it decreases by. Okay. And then we're going to again do that same thing. So we're going to be like 608 minus 475. And again, as you're taking a look at those, again, we are decreasing the amount, and that decreased amount is going to be now a negative 133. So like, again, that's the change to get from one number to the other. Okay. So that's like how much I had to take away from 608 to get 475. Okay. And you're going to kind of keep doing that the whole way through. Now, what we're going to do is we're going to take this number here, negative 172, and we're going to divide it by 780. Okay. And when we do that negative 172 divided by 780, what that does is that's going to give me my percent change. Okay. Now it is going to be in a decimal. So keep that in mind, ladies and gentlemen. It does give it to you in a decimal in that sense there. And so we do normally like to change it into a percentage. So this divided by this, which is going to give me basically a negative 0.220513. Again, I do normally like to change it to a decimal, to a percentage. So a negative 22 point, rounding it to this place here, which will be 1. So basically a negative 22.1%. Now, we did this kind of with the other one here. We got this negative 133. So I'm going to take that negative 133 and I'm going to divide it by 608. Again, taking what was originally there at the beginning of that second month and what was it decreasing to get to the next month? Like, what is that percent change? Okay. When I do that division and then multiply that answer by 100, that gives me basically a negative 21.9%. Okay. And that is my percent change for that one there. And again, we can constantly do this for all of these. So I'm going to erase all of the ink here. Okay. And so again, if I literally just take that difference there each time, like what is it actually increasing for? So that's where the percent differences come from. And then again, I always take this number and divide it by the output, that the first part of the output, the larger the output that I'm subtracting it from. So like this one, I'm going to divide by this. And that's where I got that negative 22.1. I took that negative 133 and divided it by 608, which is where I got this here. So if I take a negative 105 and divide it by 475, again, that's going to be where I'm going to get the negative 22.1% here. And again, that's my percent change. And as we take a look at that percent change there, we begin to notice it's kind of similar, like we're in between like 22 and 21, like 0.8 to 22.2. So we can kind of see they're very similar, but as we are looking at those, that is actually not 100% perfectly the same every single time. So in our case there, that would tell me that pretty much like, okay, fine, your percent is got to be approximated. So like we're probably going to use a model here. Okay. Now, for the most part, again, are you guys going to be doing these percent changes yourself every single time? No, this is not something that's very common. People normally just throw the data into a calculator and the calculator does everything for you. And you can kind of be like, oh, well, it wasn't a perfect R of being 1 or -1. Okay. So basically this means that we can see that it's approximately around 22% less every single month. So it's close, but not perfect. So let's actually plug all that data into the calculator and let the calculator do the model. Hopefully you've already put, again, if you haven't, take a second, pause it, and plug all of this data into the months being my list 1 and the sales being in list 2. Okay, since you've already paused it and you've done it, so now you can actually get that model. And your model should be basically looking something like this here. And again, it's going to give you the model itself. So guys, do remember that you're not actually figuring this out by hand. The calculator is going to just kind of give it to you. And this is where you ran that exponential regression. Okay, so you plug stat, edit, plugged all the stuff in list 1 and list 2. And then you go back to the stat button, arrow over to the calculate menu. And then you choose option 0, which is the exponential regression, which gave you kind of, like I said, this formula here, y equals a times b to the power of x. Again, my b to the power of x is this going to be that kind of 0.780 to the power of x there. And then they're going to give you an approximate a. Okay. So as you're kind of working your way through this, again, this is kind of what's really, really cool. We can kind of see that it is kind of decreasing. And if I plug that into the graphing calculator and actually graph them on the same axis there. Okay, so let me go ahead and graph both all the scatter plots and the actual model here. And when I do that, it looks super cool and we can kind of see that it does work pretty well. And remember I said like those percent changes were pretty close, all really close to each other. So since they're all really close to each other, yeah, we can see that like it hits most points. But again, it's kind of a decrease. And again, we did see that decrease because again, those data values did go down every single time as I was working my way through them. Okay, so let's actually look at just what exponential models are itself. Now, if they tell you it's a constant percent change, which again, is not 100% realistic if you have data, but if you're trying to just kind of model with it being a constant percent change, the formulas are as follows. Okay, now again, I just want you guys to go ahead and make sure to have these written down. And again, this first one here, if there's a plus sign, this is going to be my growth. Okay, so this is going to be my exponential growth. Sometimes they don't like to use the word growth. Sometimes they like to use the word like increase by. So we know there we've got our increase. The one with the minus, that's going to be our decay. Now, again, a lot of times we don't use the word decay here. We normally use the word like decrease. Okay. So like an exponential model here, these are kind of our base ideas. Now in the calculator, when you were doing them a moment ago, the formula looked a little bit like this here. And basically, ladies and gentlemen, that B value that the calculator spits out is basically what the 1 plus R is, or the 1 minus R, depending on what they are. Previously, let's think back to what we were just doing a moment ago. Remember, I said it had about maybe a decrease of about 22%, right? And so if I were to basically take 1 minus 22% there as a decimal, which would be 0.22, notice what that does is that basically gave me a 0.78. Okay. Again, let me go back a slide. Take a peek at that formula, and there we have it. So like I said, the calculator is kind of doing this formula for you, which is kind of really cool. So it's giving you that B value of that either 1 plus A or 1 minus A. Now it knows it's minus in our case here because we were decreasing. Okay. But not every problem is going to have all of your data in a table. It might just say, oh, we'll use this decrease percentage. Okay. Say that some item increases in value every year due to inflation. So we're increasing in value. So that's going to be increase or growth. So that'd be this model here. Or I don't know. Before, previously, you know, a lot of times the moment you drive a car off a lot right after you buy it, brand spanking new, it loses its value, and it actually continues to lose its value kind of pretty exponentially at first. So I would use the one with the minus on that one. Okay. So suppose you've got inflation and it averages 6% per year for each year from the year 2000 to 2010. This means that if you have an item that costs $1, 1 year later, it's going to cost $1.06. Okay. Now, in the second year, that we're literally going to take the item now costs $1.06, and we're going to increase it by another factor of 1.06, which means it ends up being basically like 1.06 to the second power there. So pretty much after 1 year, we had $1.06. After 2 years, it'll be $1.12. And after 3 years, again, as I continuously go up in years, it's going to go basically be $1.19. Okay. So we're going to start by actually writing that expression. And we're going to start with, well, what if the initial cost was $1? And then in part B, we're going to again do the same thing, but except for the initial cost be $100. And then part C, we're actually going to use a model that we create. So let's write an expression that gives the cost. So as I go back, I'm going to go back real quick here, and I'm going to highlight a couple of things. So the first thing I'm going to highlight is what our average percent per year is. Again, they use the word inflation, which inflation means an item goes up. They kind of give you the hint in the second sentence there that it's going up. And then we also need to know what our A value is. In our case here, the problem kind of gave the A value, saying that we're going to let the item cost $1. Okay. So now that we've kind of got our key ideas there, again, these are kind of the ideas that I need. But in nowhere in the problem did it have a table. So this is what's kind of telling me, oh, okay, I'm going to create this exponential model myself. Okay. Now we have two choices. And again, remember, one is with the plus R and one is with the minus R. Now, straight away, I can tell you it cannot be the one with the minus here. And again, the reason why I know it's not this one is basically, remember, I gave you the example in the problem that we got inflation, which means the money, it kind of grows every year. Like there's this inflation means increase. So this is our formula problem that we're going to use. We also know that our initial amount is $1. We also knew that our rate is 6%. Again, we do not again, keep that in mind. We do not like to keep that as a percentage. So we're going to change that to the decimal 0.06. Now, X basically is just going to make a magic transformation into a T because again, it says T years after. So make sure you're plugging in the right letter there. So we have $1 times 1 plus 0.06 to the power of T. And again, I can kind of add these together, which is going to give me $1 times 1.06 to the power of T. And again, 1 times anything basically is just that anything I'm multiplying it by. So I'm going to kind of just drop that 1 in the very front there and just get my 1.06 to the power of T. Okay. And there goes that model. Now, it's not bad. And again, this is always going to be like a 1 plus that percentage there. Now, what if I ask you to take that model, but this time I want you to do it where the starting cost is $100. So again, we're still using that same base idea here. Okay. But instead of A being $1 this time we're going to make it $100. My R is still that 6%, which again, we're going to transform into the decimal format. And instead of X, we're going to change that to a T. Okay. So basically we get Y equals 100 times, and again, this is 1 plus 0.06. So that's going to be that 1.06 to the power of T. And there goes that final answer there. Okay. Once you've plugged all that in, then you just got this like really nice formula, right? Now we're going to take part C, and part C says we want to use that data that you found, that model that you created in part B for estimating maybe what is that future value for the year 2010. Okay. Now I'm going to go back one slide just because I need to point something out real quick. Okay. And again, the reason why I'm going to point this out, and again, this is stuff that you've been warned of. T is the number of years from 2000. That's very important to make note of that. Okay. Now, the reason why I say that's super important to make note of is because in our case here, we're using the year 2010. So remember, T equals 0 is 2000. So how many years have actually passed is going to give me 10 years, right? So we're going to take the model that we created and just plug in 10. So we have 100 times 1.06 to the power of 10, which gives us about $179.08. And again, I'm rounding 2 decimal places because it is US money. Okay. Now, notice what's a little different from this one versus last one. The last one actually had no table, which meant the calculator was just going to be great for just like punching, adding, and subtracting numbers. Whereas when I've got a table like this, again, I'm going to plug stuff in. Now, as I start to plug stuff in, one of the things that I want to kind of look for in the problem itself is somewhere in the problem. And again, I'm not 100% sure where it is, but again, it's always somewhere in the problem. It's going to give you X is the number of years since blah, blah, blah. Because we don't really like when we use years, list one, we don't like to actually plug in 2010. We would like to actually make adjustments to that. Okay. And again, keep this in mind that this is my list 1, list 2, and a repeat of list 1, list 2. So you should have a total of 9 items in list 1. And again, do not type in the year. If you do, you're going to get it wrong. Okay. So we're going to use this model to do a logarithmic model first. Okay. Okay. So since we're going to do a logarithmic model, all the stuff is still the same. You're going to put your first list in list 1 and then the percent in list 2. Okay. So if you need to pause the video and plug this stuff in your calculator. Okay. And then we're going to run our regression. And again, guys, do remind yourself, it's use the word logarithmic model. And again, logarithmic model, I can use the word also logarithmic regression. That is going to be choice number 9, which is the one that says LNREG. Okay, linear regression. That is the one that we choose when we see the word logarithmic model. Okay. Again, the calculator is going to do that math for you, and then it's going to spit back out an A and a B. Now make sure that you are writing down everything that you have that's in the calculator. And then from there, you just kind of want to take it and roll with it. And you normally have like a second part where you're going to plug into it. Okay. So if you were to plot it, this is what it's going to look like. Here's my logarithmic and the shape it's got. Again, remember that exponential, we kind of had this shape was exponential, or if it was increasing, it kind of did this shape here. So this is a little bit different. Like it looks like it flipped. And again, logarithmics are pretty much, I shouldn't say are pretty much, logarithmics actually are the inverse of exponential. So as well as inverses, a log is an inverse of an exponential, and an exponential is an inverse of a log. So they do have that beautiful relationship. Okay. And again, we can see it's a pretty decent fit. Okay. So use a reported model to predict the percent of US adults with diabetes in the year 2027. Again, remind yourself that you did not plug in 2010 in the calculator. You plugged in 10, 15, 20, and so on. Because again, this was my list one, and we don't talk about it in terms of the year. We always say the number of years since something. So in order to plug something in the model, you're going to have to plug in something besides 2027. And again, our model, basically our 0 year was 2000. So 2027 is 27 years later. And all I have to do is plug that in the calculator now with my model itself. And again, with that beautiful model, we see that we have there a negative 12.975 plus 11.851 times the natural log of 27. Again, that's going to be approximately 26.1%. So in the year 2027, according to the model, we should have about 26.1% of adults reported with diabetes. Now, part C says, in what year? Okay, first of all, this is slightly different in the wording, and that's really important to note. Okay. In what year does the model predict that the percent will be 26.9%? Okay. So the first thing is that I highlighted in what year because that's really important to note that this is T. This is the time, or AKA X. The model is going to be something that you did with the calculator majority of the time. And then this right here, this is basically my Y value. Okay. So you have a few different options for these. And again, we've spent a lot of time with these previously. So you're basically going to plug in Y to be that 26.9. And then you've got it equal to that negative 12.975 plus 11.851 natural log of X. Again, in what year, depending on the problem that you're looking at there, it can be T or X. It just kind of depends. So either way. And then you're going to use what we did in previous sections to solve it. Now, again, you still have the option to plug at this point right here. You could have plugged into Y1 and Y2 and split it in half and then find the intersection. That is also an option for you if you don't want to do it fully by hand. Okay. So and that's what I'm stating down there at the bottom. And you'll get the exact same answer basically at approximately 28.9 years. Okay. Which would make it basically rounding that to the next year up. Again, I don't ever care what this is. We round it up. So it will reach about that 26.9% of US adults with diabetes in the year 2029. Okay. Again, we can take a look at, let me go ahead and erase my ink there. Take a look at what that graph looks like. Okay. So again, here we've got a beautiful table. Again, if you've got a table, guys, you automatically know that you're going to have one part of this is list 1 and the other part is list 2. Now remember, because it says the word year, we're going to need to tweak. Okay. I didn't even really fully read the problem yet, and I'm already seeing that this is what I'm going to have to do. So the table contains the total percent of labor forces that is female for selected years from the years 1900 and projected to 2050. So again, 1900 is probably my 0 year there. So again, remind yourself that what we're going to do is we're literally going to plug my list one values. This is going to be 40, then we have 50, then we have 60, then we have 70, then we have 80. And then again, over here on the other side here, we have 90. Now for the year 2000, guys, again, we always subtract it from our 0 year. So we're actually at 100 here. And then we have 110, 120, and then 130. Okay. Once you have that all plugged in, now we're going to start by actually finding the models itself. So our first model is going to be logarithmic function to model it. And then we're going to kind of look at that graph, and then we're going to assume that the model is actually valid for the year 2024 and use it to estimate the populations. Now I say assume it's going to be valid because again, it says it's projected for all the way up to 2050 there. Okay. If you need to stop here and pause and actually plug in your list one and list two values, that's perfectly fine. And then come join me in a second. Okay. So we're going to start with the model itself, which again, remind yourself that what you're going to do, again, anytime I've got that, I'm going to plug all my stuff in list one and list two. Then I'm going to hit stat, arrow over to calculate, and go find the logarithmic regression, which is again, number 9. Okay. So number 9 is that linear, or sorry, not linear, a logarithmic regression. And again, it's the one that says LN because it's a natural log regression. So we don't actually want to say natural log regression every time. We're just going to say logarithmic. Okay. And again, there's really not a lot of work for you guys to do. So I can't like stress that the calculator is doing all this work for you. Okay. We're going to plug it in the graph and let's take a peek at it. Again, as we take a look there, let's comment on how well the model actually looks. One of the first things I begin to notice is that as I plug in my scatter plot and turn my scatter plot on, and then again here, remind yourself that anytime you're looking at these types of things, you're going to need to adjust the window. So if if you can't see all this, again, window adjust real quick for the calculator is literally, you're just going to hit the window button and look for stat. So look for Z stat. Okay. If I'm not mistaken, it's down there. I think it's number 9. So just kind of keep that in mind. Okay. And remind yourself that you can always manually adjust these yourself. So if you want to manually adjust, that's going to take a little thought process on your side. But basically the stuff that we like to kind of manipulate them, and these are really the only 4 things I like to manipulate. You can adjust the scales if you want to. I just don't like to mess with them. So my X-Men, normally I would plug that at 0, just so like this goes all the way to 0. And then my X-Max, we know that it was good until at least, over 100 and something years later. So I would go back to my data and go, oh, let's see, it went all the way up to 130 here. So let me go to like 140. Okay. And again, that's kind of like how we make these decisions of like what it looks like. If you want to do the auto adjust, this is the auto adjust. Okay. Manual adjust is kind of, you're going to have to use your brain a little bit. Normally, because this is talking about percentage of something, I'm going to start with 0 and then go up to 100. If you feel like 100 was too high, you can always kind of come back down. So 50 would work. And again, why did I go from 0 to 100 on the Y's? Again, it was a percent of something increasing or decreasing, and percentages are normally out of 100. Okay. Okay, so now that we can see that, the model doesn't look perfect. As I'm looking at this model really closely here, again, what do I mean by that is like, and these are kind of off, and then these are kind of off. So we can see that the model is not really that perfect of an exponential. Exponential would be kind of, the concavity would be different, but a logarithmic, it's close, but ain't no cigar. So this would be where I'd maybe explore a couple others, but it's not horrible. Okay. So let's assume that the model is really, really accurate and valid. And let's figure out what it would be. What does it actually estimate for the year 2024? So the first thing I need to do is, again, make an adjustment to 2024. And again, remind yourself that the 0 year was, I misspelled you there, sorry, was 1900. So that's my 0 year. So after the year 2000, there was 100 years already gone by. So we've got another 24. So that's where that 124 comes in. Okay. And then all you're doing is plugging it in. That's all you do. Plug it in the model. And you're going to get that. Sorry, I meant to go back a page. And again, this is that model. That's all you're plugging it into. So right here, I'm going to plug in 124. Okay. And this is what I ended up with, which was about basically 50%. So based on this model, it'd be around 50% of women in the labor force. Okay. With this one, again, guys, ladies and gentlemen, this is just going to be a lot of calculator. So this should not be a new section for you guys.